Hello and welcome back to Differential Equations, section 3.3 on homogeneous equations with constant coefficients. So our equations now are going to look like those equations where you have your, let's start with y to the nth degree plus p1, need constants, constants. A0 or an, and then an minus 1 y n minus 1 derivative plus an minus 2 y n minus 2 plus dot 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 all the way down to a0 y equal to 0. That's the homogeneous part. There is no forcing. Now the rest of the chapter 3 is going to be about forcing, and that's going to be after our exam. So we have the constant coefficients over here. These A0, A1, A2, dot, 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 all the way to AN are all constants. The solution is going to be given as y, let's say of t, or x, whatever, is going to be C1 e to the R1t plus C2 e to the R2t plus C3 e to the R3t plus dot 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 plus Cn e to the Rnt if there are, well, let's say if all R's are distinct. Now, why is this? How is this? Well, we can actually build up to it. If I say the first order dy dt, first order equation, let's say you have dy dt, well, let's write y prime plus y equals 0. So this would be the first order linear equation, and we can solve this using our method of separation of variables, for instance. So you can go and you can say dy dt is equal to negative y, and then you have your dy over y is equal to negative dt, and when you integrate both sides you get your ln y in absolute value is negative t plus c, and then when you e both sides it works out to be y equals e to the negative t, and then this c becomes a constant in front. So you can call that C1 or whatever you want to call it. C1. How about that? So we learned that if you have a first order linear, right? So this is the first order or the linear ODE. We learned that the solution is of the form C e to the RT. So that's the form. So now what I can do is I can use that assumption to solve higher order, and then we are going to, now I'm going to give it a name, that our equation is called characteristic equation. We are going to get that characteristic equation, which later on we just use as a shortcut. So what is the method if I am to have, let's say, y double prime plus 3y prime minus 4y equal to 0. If you assume that your solution y is equal to some c e to the r t, right? You are assuming that because that's what we got when we solved the first order. So you say, would this solution be good for any order? And you find the derivatives of this, right? So y prime is going to drop down this constant r, so it's going to be c r e to the rt, and then y double prime is going to be cr squared e to the rt. When you take another derivative, it drops another r down. R times r is r squared. When you plug all of those in, you get, instead of y double prime, you get your cr squared e to the rt plus 3cr e to the rt minus 4c e to the rt equals 0. What can you factor? You can factor ce to the rt, and what's left in parentheses? R squared plus 3r minus 4 equals 0. And there is your characteristic equation. And if you take a look at the characteristic equation here and your differential equation, that's pretty much like, oh, we just swapped those r's, right? So that's where the characteristic equation comes from this calculation that you can actually always do, but you don't have to because it's always going to work that way. So we learned the shortcut to jump from here directly into the characteristic equation, which computes our r's for every single one of these. Now, if I'm looking to solve this entire equation, clearly c equals 0 is not going to give us anything. ERT equals 0 has no solution. And the only thing that you can look at is the characteristic equation. So that's why when you divide both sides, right, if you divide both sides by ce to the rt and ce to the rt, right, it still stays 0. On the left-hand side, you only have the characteristic equation. So that's where the characteristic equation comes from. That's why you can jump immediately from your differential equation into this. And the best thing ever, right? It works for every order of differential equations out there. So it works for literally everything. So now, if I have distinct roots, meaning all r's are different, then this first theorem here kicks in, and that's it, the roots are distinct, and you have your solution just by simply converting your differential equation of whatever order it is into this characteristic equation with r's, and you solve those r's. If r's are distinct, you just write out the solution, and then, right, if you have the initial conditions, right, good luck with your matrix, right, to compute the, what do you call it? Coefficients, right? Constants. All right, so now we can quickly solve this problem because my characteristic equation is just this, and it's something that it's easy to factor. R minus 4, no, plus 4, R minus 1, and that gives me R is negative 4, R is positive 1, and that immediately tells me that the solution is C1e to the negative 4 plus C2e to the t. That's it. We're done. There is nothing. Obviously, if initial conditions are given, you can compute your C's, but we are done with solving differential equation. As easy as equation converts into characteristic equation, you factor it, and then you just write the solution. It's 1, 2, 3. and it should not take longer than 2 minutes. I mean, if you can't factor, obviously, it's going to take longer than 2 minutes.
It should be negative 4t there, right?
Negative 4t, yes. Thank you.
Okay.
Yes, negative 4t. Yes. Awesome. So you guys have the distinct roots down. Now we go for repeated roots. Now, these can be, as you saw earlier, they can be mixed with distinct, but the rule for repeated roots is going to be you are multiplying by t. So now, when you have your repeated roots, your solution, the process to solve doesn't change, it's just the solution changes. Y equals C1 e to the RT plus C2 t e to the RT plus C3 t squared e to the RT, and I'm just going to go plus plus this way, right? Because you see that you have your no t, or t to the 0, which is 1, and then t to the first power, t squared, t cubed, t to the fourth, right? And so on. So if you have 3 repeated roots, then you would have this to be your solution, right? You will go up to the square. So repeated roots are like that. And we had earlier, I had that example with the cubic. But you can literally have anything else. So if my equation worked out eventually to be r minus 3, let's say, to the fourth power equals 0, then r equals 3 with multiplicity 4. And in that case, my differential equation solution will be C1 e to the 3t plus C2t e to the 3t plus C3t squared e to the 3t plus C4t cubed e to the 3t. And that will be the end of it, right? Because it was a fourth order equation, we have 1, 2, 3, 4 solutions. And this increasing t is the one that makes sure that the Wronskian gives us, right, independent. I mean, Wronskian is used to check. It's not Wronskian that gives us. We use Wronskian to check that these solutions are linearly independent. And we have 4 solutions in there. So this is also something that we talked about before. And, if you want to work out one of the maybe full examples here, we can quickly come up with, y double prime. This is like a standard stuff for your course. So y double prime minus 18y prime plus 9y equal to 0, right? So if this is your problem, second order linear constant coefficients homogeneous because it's equal to 0, then what you do is you convert this quickly into your characteristic equation, and then you once you convert this to characteristic equation, you factor it, but this we're gonna be r minus 3 squared. Oh wait, this is supposed to be not 18, it's supposed to be 6, right? Because it's times 2. Yep, it's 6. 6, 6, 6. There we go. All right. So now we have that r is 3 with multiplicity 2. And you're writing your solution quickly. E to the 3t plus C2t e to the 3t, because repetition, right, gives you that extra piece there. Again, given initial conditions, you differentiate, plug everything in, and calculate your constants. This is the stuff we covered so far. It was part of 3.1. It was part of 3.2. It was part of 3.3, right? So all of this stuff is there from before. What's new for 3.3 is complex roots. Well, we also complex roots. We also explained why that characteristic equation works. That was also new, right? So you understood where that equation came from. It's not just someone rewrites a differential equation into a polynomial just because it occurred in their dream or something. It is all derived mathematically, and you have seen that derivation. So now we want to see what happens if we have the complex roots. Now, for complex roots, we are going to have trig to take over for our solutions. So if the roots are of the form, usually we write z's for a complex, but I'm going to write r because that's what you are used to. If r is equal to a plus minus, well, I'll just put the standard one, bi. You have seen these numbers before, like 3 plus 2i, 4 minus I, and stuff like that, right? So complex roots. If you have a complex root, then the solution, and complex roots are always in pairs, so it is a plus minus situation there. It's called a complex conjugate. The complex roots will give you e to the a y equals e to the at, and then in parentheses you're going to have c1 cosine bt plus c2 sine bt. And now this completes your set of possibilities when you factor quadratic. When you factor quadratic, you can get two real distinct roots, two repeated real roots, or two complex conjugate complex numbers. Those are the only three possibilities that you can get when you factor quadratic. And that's where the story ends, right? Because if you have a cubic, once you find one solution, the rest is quadratic. If you have a equation that it's a quadratic, right, the fourth degree, then once you find the first two solutions, the last two are quadratic, so they can be complex and so on, right? So this is what we have for our complex roots. That's the way. Now, derivation for this is using Euler's formula for e to the I theta is equal to cosine theta plus I sine theta. And those calculations are obtained also from the characteristic equation where you cannot factor. So an example of this would be what we call the wave equation, y double prime plus y equal to 0. This is a two-dimensional wave equation because it's going to end up being a trigonometric wave, which is the solution. If you convert this to your R characteristic equation, you get something that you cannot factor over real numbers. So this factors into like R squared is equal to -1, from where R squared equals to square root plus minus, right? When you square root both sides, and you get that your R is equal to plus minus I. Now that is R equals 0 plus minus I. So your A is equal to 0 and your B is equal to 1. And please don't make this complicated. Just plug those numbers where they belong. Right? There's no reason to think and invent something new. you have your A in a formula, plug that zero in, and you have your B in a formula, plug the 0 in, right? So our solution would be y of t is equal to e to the 0 is 1, so there is no e because there is no real part, right? This is the factor, and this is me trying to show algebra and basics. And then, so there is no, a is 0, and because a is 0, we are going to get e to the 0. So you are only left with c1 cosine 1t, which is just cosine t, plus c2 sine t. And this is some kind of a wave, right? If you know what c1 and c2 is, right? You have initial conditions, you know, c1 or c2 could be 0. You can just get a pure sine function or a pure cosine function or the combination of two of them, right? And get all kinds of interesting waves and so on. You can get a whole bunch of things depending on your C's and a whole bunch of other stuff that comes up, right? So all you need to do again is write the characteristic equation, factor it in any way you can get your complex numbers. And if you don't know factoring, well, you can always use, right? You have ax squared plus bx plus c equals 0. You have your characteristic equation. Sorry, your quadratic formula. So r, and then r was going to be negative b plus minus b squared minus 4ac divided by 2a. You are going to get negative under the root, and that will give you complex values. So let me see if I can quickly figure out which problem in the book will have that situation. Now your book has the second order, fourth order, third order. They have all kinds of equations here because, right, they can. B squared, that's gonna be 36 minus. Okay, looks like problem 8 is one of our complex problems. It said y double prime minus 6y prime plus 13y equal to 0. They do not give us initial condition, which means we will not be able to compute C1 and C2. Convert into R's and then unleash the formula, right? The quadratic formula to come up with a solution. And I will be right back. So try that for next 3-4 minutes, and write down the cosine solution. Given you will have your A, you will have your B. Okay, let's take a look at this together. So we have negative b plus minus b squared minus 4ac divided by 2a. 6 plus minus, that's 36 minus 40, 52 divided by 2. And 6 plus minus this 52, that gives us square root of negative 16. And then we have a 6 plus minus 4i divided by 2, and that gives us 3 plus minus 2i. So your a is 3 and b is 2. And you just write the solution. Y equals e to the 3t c1 cosine 2t plus c2 sine 2t. And you box your answer. Given initial conditions, you can compute c1 and c2, right? And it will be a product rule to find the derivative and all of that stuff. So let's find a problem that has initial conditions as well, so we can do that as well. Problems with initial condition. They only have 21 through 26. And unfortunately, the problem that I like is not going to be complex. Okay, let's just roll the dice on on one of the problems. See how well it works. So let's try problem 24, which has 2y to the triple prime minus 3y double prime minus 2y prime equals 0. With initial conditions, y of 0 is 1, y prime of 0 is negative 1, and y double prime of 0 is 3. There we go. All right. Now, you can be thinking about these initial conditions and saying, oh, okay, that's my acceleration, that's my initial velocity, that's my initial position, right? So yeah, that all fits whatever we learned before. So that trick gives us the characteristic equation of 2r cubed minus 3r squared minus 2r equal to 0. You see that you can kick r out, and you have your 2r squared minus 3r minus 2 equal to 0. You have your r equals 0, and now you have to factor 2r minus 3r minus 2 equal to 0. Now, let's say you do not want to cheat, right? You want to be honest over here, so you are using quadratic equation. So negative b, that's going to be 3, plus minus square root of b squared, that's 9, minus 4ac. And this negative is the one that makes this not complex. Over 4, 2a. So 3 plus minus square root of 9 plus 16 is going to be positive 25, and we are not having the complex. So 3 plus minus 5 divided by 4. So one answer is 3 plus 5 is 8, divided by 4 is 2. And the other answer is 3 minus 5 is negative 2, so negative half. So r equals 2 and r equals negative 1 half. So these are all distinct roots. They're all distinct. So I have y equals c1e to the 0t, so just by, plus c2e to the 2t, plus c3e to the negative half t. And that would be what we call general solution, but we do have those the initial conditions to calculate constants c1, c2, c3. So I need my y prime. Well, that's a 0 on c1. 2c2 e to the 2t minus 1 half c3 e to the negative 1 half t. And the y double prime is going to be 4c2 e to the 2t plus a quarter c3 e to the negative 1 half t. And now we use initial conditions. So for the top equation, right, we have y of 0 equals to 1. So the top equation gives us 1 equals c1 plus c2 plus c3. Because the zeros, when you plug in t equals 0, these e's become all 1. For y prime, we have y prime of 0 is negative 1. Okay, that's going to be negative 1 equals to 2c2 minus 1 half c3. Again, when you plug in 0 here, the whole thing is 1. And finally, the last one is equal to 3. So y double prime of 0 is 3. So 3 is equal to 4c2 plus a quarter c3. So I hope you see that you can use the last two rows to come up with C2 and C3, and then you plug C2, C3, and you calculate C1. So we are going to multiply this equation by 2 and multiply this equation by 4. So we can cancel C3s and calculate C2. I'm going to do the whole problem, obviously, without a calculator and so on, just to show all of the calculations, because you are supposed to. I mean, if you were taking this class at Rutgers or MGIT or anywhere else, they don't allow calculator in differential equations at all. So it's not even a solar one, right? You have to compute everything by hand. So if you are to do this, you'll get negative 2 is equal to 4c2 minus c3. And times 4 on the bottom is 12. And then 16c2 plus c3. When you add the two equations, you get 10 is equal to 20c2. So c2 is a half, right? c2 is a half. Then you can use negative 1 is equal to 2 times a half minus 1 half c3 to calculate c3. I use the second equation. So this puppy over here becomes 1. And when you subtract it on the other side, so this thing over here is 1. Subtract to the other side, you get negative 2 is equal to negative 1 half c3. Multiply both sides by negative 2 to get c3 alone. And you get your c3 to be positive 4. Now you have the first equation. 1 is equal to c1 plus a half plus 4. And from there, C1 is negative 3.5, negative 7 halves. That's negative 3.5. I have the solution. Y equals negative 7 halves plus 1 half e, I forgot, to the 2t plus 4e. The tablet is starting to overheat, even though I have the cooling. Negative 1 half t. And there it is. The general particular solution with the constants computed. So we have couple of these problems, and we are going to see more of this, because whatever you learned today and so far in chapter 3 is going to become just a first part of the problem later on in this chapter, because we will have forcing on the other side. We're not going to have a zero. We're going to have forcing, and there will be a completely separate calculation for the forcing to give you the overall solution for the problem. So please practice this as much as you can to come up with solutions as fast as you can, because this is going to be, about 20 or 30% of a problem coming into the second part of chapter 3. So that's after the exam, but that's going to be on exam 2, right? So, and the final, and later coursework. So we are going to deal with forcing later on. Currently, what you guys have done with these equations, and that's our next lecture, is this system, right, where your mass, the object mass, has this spring attached to the wall. That was a terrible spring, but whatever. And it oscillates back and forth. And if you remember, we had the equation that was mx double prime plus cx prime plus kx equal to 0. Our next class is to realize that, this mass connected to the spring is actually n a dash pot here to slow it down, right? So that's another side, because we have this term. Without that term, you just have a first and a last. But we'll do that next class. You do see the second order differential equation, and you can calculate the position in time, which will give you some c1 x1 plus c2 x2. And those are going to actually be complex. We will actually work the physics of this. So you will see why is the motion periodic. And the motion is going to be periodic because you have complex solutions to the differential equation here, and then the object just goes back and forth, back and forth, back and forth, back and forth, right? Periodically, we say oscillating. So that's the next time. We are going to take the first, 3.1 and 3.3, but generally 3.3, and apply that to our mass spring system, and develop the application for this, and eventually at the end of the course we'll apply it to RC, RLC circuits, right? R resistance, L inductance, and C capacitance, to develop equations and a way to solve this with that as well. That's the 3.3. Any questions, concerns? Yes.
Just one.
You
Will the ROM schema, it doesn't take place in the complex roots, or
Oh, it does, my friend.
Oh, okay.
Yes, except the Wronskian for the complex. Well, thank you for mentioning that. So the Wronskian for these complex roots is literally, lock your doors and hide your children, okay? Because remember, your solution for the complex is, oops, well, I'm going to actually erase this stuff because we're going to have an hour and a half of this stuff next class. So now that you mentioned Wronskian and the rest of the classroom should just thank you for that publicly. Your solution is now e to the at c1 cosine bt plus c2 sine bt. What does that solution looks like when you break it down into two separate solutions? It looks like e to the at, c1 e to the at cosine bt plus c2 e to the at sine bt. So your Wronskian now has these product rules in, right? Now, luckily, you can't go with a Wronskian more than two because complex is only complex pairs. So you can only have two of them, just like Sith lords, right? I mean, like Sith, you only have a master and the apprentice. That's it. So you will have your e to the at cosine bt and e to the at sine bt. And here is going to be the derivative, which is the product rule. I don't know if I should separate this like that. You're not supposed to put this thing in a matrix, but I want to have the row for functions and the row for functions and the row for derivatives. There we go. So now you need a product rule here. Copy the first, derivative of the second, that's going to be negative b sine bt, plus copy the second, which is cosine bt. Derivative of the first is a e to the at. So that's what the Wronskian looks like for the first one. Then you do the second one. Again, at, derivative of the other one is going to be b cosine bt, plus copy the second one, which is sine bt, and the derivative of the first a e at. There we go. And then you go. It's all easy stuff, but it's very picky, annoying. There you go, annoying calculations, a lot of algebra, right? But the concept for Wronskian will always be y1, y2, y1 prime, y2 prime if you only have two solutions. So, oops, tablet is overheating, so it's behaving, it's hard to write. So over here, you distribute your E, and here is your C1, Y1, C2, Y2 from complex. Very good question. Thank you for asking. Well, actually, the rest of the classroom should. Thank you for that, because if I put, Wronskian for complex on the test, obviously, right, you should be able to get it from here and just know the algebra, but now you have seen it done, actually, so there's that. Good question. Anything else?
So when we're doing the complex roots, how do you know, because B could be positive or minus, right? So how do you know what to make B?
Okay, so the B is always a positive value because that plus and minus is actually worked into from the theory, and that's why one is sine, one is cosine. Okay, so you will only, we do not, right, the complex number goes like this. So B is always positive and A is always positive. I mean, A could be a negative number, but the B will always be a positive value. B is always positive, where A could be, so if you have, let's say, if you have negative 3 plus minus 4i, your A is negative 3, your B is 4.
All right, what if
B
you
is
have,
always positive.
okay, I see now, yeah, got
Cool.
it.
All right. So A, you have to take whatever is there, and B is always going to be a positive value. Cool. All right.
I have another
And
question.
yes.
For the complex numbers like the I, if you had like square root of -18,
Okay.
could you like change that to 9
Yes.
or 3 root 2?
Yes. We are going to follow the algebra. -18 is going to be square root of -1 times 2 times 9, and then -1 gives you I, 9 gives you 3, and root 2 stays there. Yes.
Okay.
And then your B is 3 root 2. Very good. Anything else? As my voice cracks. Anything else? Going once. Going twice. All right. Well, that was efficient. Excellent questions. And next class, we are working on mechanical vibrations. So we are going to take these complex roots and give them meaning in mechanical engineering. Eventually we'll do electrical as well, but for now just mechanical. See you all on Monday, or if you join earlier, yeah, next class is Monday.
Next class, will we set the test date too?
Yes, so
Okay.
everyone better be in class if you want to vote for the weekend, right?
Okay.
If you're not there, you're not voting, you will have to do the exam, whatever the others picked. All right, bye.